So now that all of my spectra are referenced and phase corrected and baseline corrected, and all that pre-processing is done, now we can actually get into the business of assigning all the proton and carbon signals in the spectra to their corresponding location in gemcitabine. One of the things that's often hard to do when you have two-dimensional spectra like this is it can be hard to figure out where it is you even want to begin. You have such a wealth of information in front of you that it can be kind of daunting to figure out where do you even start. You have a proton here, you have a carbon, we have a CoSy, we have an Hsqc, and we have an HMBC. So how do I pluck out some part of this molecule that I can identify first to then use that to assign the other fragments? And the way I see it, there are two really good entryways into this molecule that can help you grab onto a spot. And they both involve using the Hsqc spectrum, so showing single bond proton to carbon correlations. All of these cross peaks are a one bond correlation between a proton and a carbon. So this is showing me which protons are on which carbons. And you'll notice that I have 3 proton signals in this molecule, 2 hydroxyls and an amine, that are not going to be on carbon. I should have 3 proton peaks that don't correspond to a carbon anywhere in the molecule. The other thing you might notice is I've drawn out these 2 protons, protons 11 and 12 explicitly. The reason being that you may notice those are next to a chiral center. Those protons are diastereotopic. We would expect them to give 2 different shifts as 2 different 1H signals in the proton NMR. When we look in the Hsqc, the tip-off for which protons are the diastereotopics should be that we see 2 peaks on a single carbon atom. That should be the only case of that we have in this entire molecule, because these should be the only diastereotopic protons on a single carbon. Personally, I used the heteroatoms to get started on this molecule, so the first thing I'm going to do is go looking for those. So if we look in the spectrum, we can see that there is a signal at about 7.36, 7.35 ppm that has no cross peaks in the carbon NMR. We can see that this signal here at about 5.2 or so also has no cross peaks, and there is Amnova's plucked out a peak here, but that is, let's see, there's a tiny little peak right here, but that's fairly dubious. What that more likely is some longer range coupling visible from this proton here. We can see from all the other peaks that they're fairly prominent, obvious things. And so the other heteroatom proton we have in the molecule is this doublet here at about 6.2 ppm or so. So going back to the proton, we want to find those signals here. We can see that the doublet at 6.2 is right there, the triplet at 5.19 is right there, and then our last heteroatom peak was this signal here at about 7.36, which is also a doublet. So the question is, how do I tell those two apart? Well, thankfully the integration should do that for me. I have 2 signals, proton 8, proton 10 on the hydroxyls that should be 1H's, and this signal here, the NH2, number 20, should be a 2H. And so right away that should tell me what the amine protons are. The only 2H signal I have that is a heteroatom is this set right here, and what's weird is that Amnova's reporting that as a doublet. And in actuality, it isn't a doublet. There are no neighboring protons here on 16. So what that actually is there's actually a lot of double bond character in this carbon-nitrogen bond from 16 to 20. So what ends up happening is that there's a fairly prominent resonance structure where these lone pair electrons on the nitrogen dump in to make a double bond from 16 to 20. These electrons in this pi bond here would move up to the nitrogen, And what that means is there's so much double bond character in this that these protons are actually spending a lot of time locked in place, not able to spin, and becoming diastereotopic. So that's the actual reason that this is showing up as a doublet, and in fact it's not a doublet, it's two 1H singlets. But that oddity being aside, it's the only 2H signal I have not on carbon, and given my molecule, it's really the only possibility. So I'm going to go to the Assignments tab here in MNOVA. I'm going to hit Manual Assignment, and I'm going to click on that doublet there and assign it to Proton 20. Now I have to figure out which of these two hydroxyls is which, so this doublet here at 6.2 or this triplet here at 5.19. And you may notice that I actually have coupling to my heteroatoms, and the reason for that is that this was taken in really dry DMSO, so there's no water around here, there's no proton exchange with the solvent, so I'm actually seeing coupling to and from my heteroatom protons. So that means that since we see the coupling, we can actually already fairly confidently assign which of these is which. So a triplet here would be my OH with two neighbors, likely that one. The doublet here would be my OH with one neighbor, likely this one, number 8. That's probably the case, but just to be sure, what I'm going to do is I'm going to verify that confidently by using what I mentioned was the other good handle into this molecule, which was the diastereotopic protons here. I'm going to go use the Hsqc to find those by finding the only two protons that are on the same carbon. And if we look, we can see that there are a couple of peaks right here on the same carbon. So yeah, these two signals here, 58.8 in the carbon NMR, and then it's this signal here and this signal here. And actually, what we can see is that there's two signals that are really close to each other. So this region right here is actually two signals stacked up, and it's overlapping with this signal here. And if we go back to our proton NMR, we can see that MNOVA integrated that region as a 2H multiplet, when now we know because of the Hsqc that it actually isn't. It's two 1H multiplets of some kind. So what I need to do is I need to go in here and I need to chop up this integral, chop up this multiplet to divide it into two 1H signals. I'm just going to click on the center of it. You can see it's not done a great job of dividing these multiplets up, but I know what the integration should be. I know that they should be a 1H and a 1H, and you can see that it's grabbed out, it's assigned some kind of multiplet to those. But now we can at least, even if the integrations are a little bit odd, we can at least use these as two separate signals when we're doing our analysis. So we're going to go back to the Hsqc, we're just going to double check. So the more downfield side of that overlapping set of signals is a 1H on some carbon somewhere. We don't know yet, but we know that the more upfield side of that signal, going by this, and then this 1H multiplet over here are our diastereotopics, because they are the only two protons on a single carbon, this carbon here at about 58 ppm. So we can go to the proton, or we can actually make our assignments here. We can click on this cross peak and assign it to that proton. We can click on this cross peak and assign it to that proton. We don't, and you can see it's also automatically grabbed carbon number 9 right here for us as well. When we're doing the assignment, we can go to the carbon NMR and you can see it's also assigned carbon number 9 there right for us. So now we know those are the diastereotopic protons and their corresponding carbon. So again, we know because we're in dry solvent and we have good couplings that we're pretty sure that this triplet, this OH triplet here at 5.2 ppm is likely this OH number 10, because it should be a triplet from the neighboring diastereotopics. We can go to the COSY to double check that to see, do we see a cross peak from this triplet here over to the diastereotopics? And we do. So if we come down here, we can see that these peaks here are interacting with the OH right there. So that's a nice double confirmation that that proton is exactly what we think it is. So we can go back to our proton, hit the manual assignment, click on that triplet there, and assign it to the OH. By process of elimination, we now know that this doublet here at 6.22, which is the only other proton signal we have in the entire molecule, we know for a certainty that that's the other OH. There's just not a possibility other than that, so we can go ahead and click that and assign proton number 8. So now that I have my heteroatoms assigned, I have my diastereotopics assigned, and because I'm fortunate enough again to be doing this in dry solvent where I see coupling from the protons to the protons in the ring, we can start finding the proton signals here in the ring, so numbers 2, 3, and 5. Since we just found proton number 8, this OH, I'm going to use that to find the proton on carbon 3 and also to then find the carbon on number 3. So I'm going to go to the Hsqc and I want to look for what does this OH number 8 see that I haven't assigned yet. And we can see that there is a cross peak right here with this proton at about 4.1 ppm. It looks to be a fairly complex kind of multiplet, so let's go to the proton and take a closer look specifically at that peak. So it's this thing right here. And Nova's called that a multiplet, and if you're wondering, well, that's just a 1H with two neighbors. It's got a neighbor here and then a neighbor on oxygen. Why is it so complex? Well, remember that fluorine is spin 1/2, and it's going to couple to the fluorines just like it couples to protons. And the coupling constants on all of those is going to be different than the coupling constant to the protons on the carbon and on the oxygen. So this being a complex kind of multiplet actually makes perfect sense. So we can assign that peak as being carbon number 3. Or proton number 3, excuse me. And with that proton assigned, we can go use the Hsqc to find its corresponding carbon. So let's go see where is the cross peak on number 3, and we can see it's this signal right at 68.4 ppm. So we can click assign here and assign carbon number 3, and there it is. So now I know my diastereotopic protons, 11 and 12, I know my CH number 3, so those should both show coupling to the CH number 2 in the Hsqc. So I'm going to go up to the Hsqc and look for what do they have in common. What do they all couple to? Is there a 1H somewhere that they all see? And looking in the Hsqc, we're going to zoom in on this region, we can see that there is something that they're all corresponding with, and it's actually the more downfield part of that overlapping set of signals that we had earlier. We can see that this is the proton number 3 corresponds to that region, and then the Hsqc also shows coupling to the diastereotopics. So we can go ahead and assign this peak as well by clicking within that multiplet there at about 3.7 ppm and clicking that, and it should, we can see it's now assigned proton number 2. Let's go to the Hsqc. We can see proton number 2 here is already assigned, and we can see that its carbon is at about 80.19 ppm. So let's click there and assign carbon number 2, which is now assigned. So the only proton and carbon signals I have left to find in this Furan ring or on its branches is the proton and carbon number 5 and carbon number 4. And the CH on 5 isn't going to have any proton neighbors, so it won't show anything in the Hsqc. It will couple to obviously its own carbon, it will couple to the carbon on 4, but there's actually a really interesting test that we can use here to find proton number 5. And we can do it by going to the proton spectrum, and what we're going to do is we're going to go looking for a triplet. So we can see that there is a triplet right here at 6.13 ppm, And you would think, oh, well, if it's a triplet, I should go to the cozy and I should see some coupling to that triplet. And in fact, when we look on the axis of this signal here at 6.13, we don't see any cross peaks at all. MNOVA's not found any, and there are none to find, but it's still a triplet. So why is that? Well, remember, fluorine is spin 1/2, and it is 3 bonds away from this proton on number 5. So it's going to couple just like proton does with that Pascal's triangle n+1 type coupling. And in fact, we can see that it's a kind of a curiously broad triplet, and that's because the coupling constants between fluorine and hydrogen are different than hydrogen and hydrogen. So we can actually know pretty definitively that this signal at 6.13, because it's a triplet that shows no coupling in the cozy, we can actually be pretty certain that that is the proton on number 5. So just to efficiently assign that, we're going to go to the Hsqc. We're going to zoom in because we can assign the carbon that it's on at the same time. We can zoom in here and we can do a manual assignment, clicking on this cross peak and clicking on proton number 5. And so we can click on that to assign that, and there we go. We've got proton number 5 labeled and carbon number 5 labeled. So the last thing that I need to do for this ring is I need to assign carbon number 4. Well, I just found the proton on 5. I had already found the proton on 3, and I can use the HMBC to find the carbon number 4, because both the proton on 5 and the proton on 3 should both have an HMBC, so again a 2 or more bond coupling to the carbon on number 4. So I want to look, what do protons 3 and 5 have in common that they both see? And if I zoom in here, we get this really odd signal where we see that proton 3, MNOVA's missed this peak, but that's okay, we can see it. We can see proton 3 has this weird set of signals right here, and it kind of looks like this diagonal triplet, and we see the same thing from proton number 5 over here. And why is that a triplet? Well, it's a triplet for the same reason that proton number 5 is a triplet. That carbon is coupled to fluorine. So if we zoom in to the region where we saw that cross peak at about 123 ppm, we see this really crazy set of lines that looks like 3 different signals, but what it actually is it is the carbon signal of number 4. The 1 bond coupling from fluorine has divided it into a very broad triplet. So that's actually quite diagnostic. We're going to click on the center of that signal and we're going to assign that as carbon number 4. And with that, we have fully assigned every proton and carbon in the Furan ring and this small branch off of it, as well as this amine set of protons here. And in the next video, we're going to see how to get into assigning this second ring of the molecule over here, including how to figure out which carbon peak is that carbonyl. And that will be in the next video.